Alright, so this is problem 15 from section 7.3. And in this problem, we're given a special group, all of whose proper subgroups are cyclic. Remember, proper subgroup means all the subgroups of G except itself. So, if we know that all these proper subgroups are cyclic, does that mean that the whole group is cyclic? So in the book they state it as a true or false question, right? So we ask it, is it true? Does G have to be cyclic? And the answer is going to be no. How can we see that? Well, in class, I told you the best group for finding counterexamples is a symmetric group, right? Particularly the one of order 3. So let's take a look at what happens. We'll recall in class, we wrote down the subgroup lattice for S3. Looked like, okay, you have S3 at the top, you have a subgroup of order 3, and it's generated by the permutation 1, 2, 3. You also have 3 subgroups, each of order 2, generated by the 3 transpositions in the group. So there's the subgroup generated by 1, 2, there's the subgroup generated by 1, 3, and the subgroup generated by 2, 3. And sitting inside of here is the identity subgroup. Okay, so you'll notice each one of these subgroups is generated by an element. That means it's a cyclic group. So all the subgroups of S3 are cyclic groups. Is S3 cyclic? Well, how can we tell? If you're a cyclic group, that means you're generated by something. That means every element is a power of one element. Okay, well, we've written down 5 of the elements in S3. Let's take a look. We'll see first, okay, E, that just generates a subgroup of order 1. 1, 2, 1, 3, and 2, 3, they just generate subgroups of order 2. Definitely not all of S3. 1, 2, 3 generates a subgroup of order 3. Definitely not all of S3. There's only one element left, and that's 1, 3, 2. But 1, 3, 2 is actually an element of the subgroup. It's 1, 2, 3 squared. In fact, the subgroup it generates is exactly the same subgroup of order 3. So no element of S3 generates it. It's not a cyclic group. A different way to see that would be the following. If S3 was cyclic, well, then it would be an abelian group, right? Every cyclic group must be abelian. If everything looks like a power of one single element, then, well, what would it mean? X to the I times X to the J? Of course that equals X to the J times X to the I. So cyclic groups are always abelian. So if S3 was cyclic, it would have to be abelian. And I claim it's not. Why not? Well, just test it. What happens when I apply, say, the permutations 1, 2, and 1, 3, or the permutations 1, 3, and 1, 2, to say the number 1? Where is this going to do to the number 1? It's going to send, well, let's see, 1 would go to 3, and then 3 would be fixed. So this sends 1 to 3. In fact, the product of these two is 1, 3, 2. How about this guy? What does it do to the number 1? Well, it sends 1 to 2, and then 2 is fixed. So 1 actually goes to 2. And in fact, the product of these is 1, 2, 3. It's not the same. S3 is not an abelian group. And so it can't be a cyclic group. Now, S3 is a good counterexample here, but it's not the smallest one. In fact, there's a smaller group than S3, which is non-cyclic, but whose subgroups are all cyclic. So recall in class we wrote down the light switch group. You have, in this case, 2 light switches, and I want to know all the different ways that we can toggle these switches. And we figured out that the answer was going to end up being the group C2 cross C2, the direct product of 2 cyclic groups of order 2. And the subgroup lattice for C2 cross C2 looks like this. There are 3 subgroups of order 2. They're all cyclic. They're just generated by they just have the identity and the one other element. And then you have the identity on the bottom. All of the subgroups are cyclic, all the proper ones that is, but the entire group is not cyclic. So this theorem is decidedly false.